Hey guys, just give me 5 minutes, okay? My laptop is giving me some trouble, so I'll just try to figure it out, and in 5 minutes I'll start the class. Okay? Sorry for the inconvenience.
Is the screen visible? Can anyone confirm? Okay, now? Yes. Thank you, Amber. Okay. So, welcome everyone. Welcome to Fuzzy Sets, Logics and Systems and Applications. And today we are in our week 11. And I'm your teaching assistant. My name is Saladi Pravalika. I'm a PhD scholar from the Indian Institute of Science, and I'm also a Prime Minister Research Fellow and CRTA. So before we get started, let's just go to our instructions. So this session is being recorded and this recording will be uploaded on YouTube, and then you can access it anytime you want until this course ends. And be respectful during the session, and please put all your questions in the chat box during the session. Okay, so the majority of the reason for this problem solving sessions is to discuss problems and uh, previous problems or problems from textbooks and all such things. But whenever like this is not my first time teaching in NPTEL, so what I have figured out is that it is better if I teach some sort of a theory in the beginning and then go and help you all with problems. So, and because of that, that's usually taking up a lot of my time, your time, and all of that stuff as well. So, that is what I have observed. So, what I'm going to do today is most of the theory part has been already covered in the NPTEL lectures. So, I'll give you an overview of most majority of the things, and directly I'll go to some of the problems that are asked as assignments in the previous years or the previous term. Okay, so I hope that's okay with you all. So since the last 10 weeks, I have been taking a different approach, but now I just want to make a little bit of change. Okay, I hope that's okay with you all. Okay, so with that, let's get started. So in the last class, we have looked at the classification of fuzzy rule-based models, right? So we have looked at fuzzy inference systems and how the fuzzy inference system works. We have understood the flow of it, right? And then came to the point where we were talking about classifications. So in this classifications, the main one of the major things is Mamdani model. Okay, so it's a non-additive rule model. So the rule model is nothing but, so we do have this rule fuzzy rules block here, right? So based on how you give your rules and all of such things and the conclusions that you draw, we have multiple models, and one such model is Mamdani model, and another one is Larson model. And these are the things that we are going to discuss in this week and in the next week. So in this week, we'll be looking at Mamdani model. Okay, so yeah. So Mamdani model was one of the first models that was developed and that was used to control a steam engine and a boiler combination by using a set of linguistic control rules, right? So for example, like I'm not telling about this, but let us say you have a kettle and you have a set of instructions, right? So when you are purchasing a kettle, what will the salesperson tell to you? So don't get water inside a particular hole. Okay, don't let the water go in when you're cleaning and all such things. So there are some certain rules that they are imposing on you. And when you take the kettle home, then you have to follow specific steps, right? You take the kettle, you fill in it in water, then you plug it in, and then you turn it on, and then you turn on the safety switch and all of such things. So there are rules, there are procedures and all such things. And similarly, even for the steam engine and the boiler combination, there are also a set of rules, okay? And those are called as the linguistic control rules, and which are basically used to control this steam engine and the boiler combination. Okay, so the rule is fairly simple. If X is A, then Y is B. So that is something that we have already seen, right? So X is a generic variable that we have been seeing since the last 10 weeks. And A here is a fuzzy value, or it can be a fuzzy set. Okay, so if X is one such thing, then Y is B. So Y here is the output and B is another fuzzy value. Or it may not necessarily be a fuzzy value, it can also be a crisp value. Okay, so if you want to read more about that, I have come across this Research Hub's article. Maybe you can go through it whenever there is time. Okay, and then we have Mamdani's inference process. So this process is same this process is similar to what we have seen in the fuzzy inference system. So first you do fuzzification, right? So in case if you're having your input as a crisp value, then you are going to fuzzify it. Okay, so that process is called as a fuzzification. And once the fuzzification is done, then you do some sort of rule evaluation. So what kind of rules are being imposed on the given fuzzy set or a given condition? Okay, so it can be two types. It can be a single antecedent or it can be a multiple antecedent. So in case if it is a multiple antecedent, but you want only one output, so you use the logical terms like and or, and then you come to one single output, right? So, so once that is done, uh, the next step that you are going to do is aggregation of output of fuzzy rules. Okay, so it's basically unification of all the outputs that you're getting of all the rules. So if you are having multiple rules, you'll have multiple outputs, and then you do the unification of all the outputs. So the input for this aggregation is list of scaled membership functions, and the output is one fuzzy set for each of the output variable. So if I'm having three output variables, x1, x2, x3, then for x1 I have one fuzzy set, and x2 I'll have another fuzzy set, and for x3 I'll have another fuzzy set. So I have multiple fuzzy sets for different variables, right? So now I want a crisp value as an output for given value, for a given output variable, right? For that reason, we'll go for defuzzification. Okay, so this is the entire process of Mamdani's inference process. Okay, so we'll look more on into the defuzzifications. Okay, so I hope you all remember when we have looked at compositions, right? We have looked at max-min compositions, max product compositions, and many other. Uh, like I just gave some other possible compositions as well, right? But when we are dealing with Mamdanis, we are going to look at only two compositions: max-min compositions and max product compositions. So for those of you who all kind of needs a small, what do you say, to make you all remember, let us say we have three different universe of discourse, x, y, and z. Okay, and then I have a relation between x and y, and I also know the relation between y and z. But if I want to know the fuzzy relation between x and z, how do you do that? Okay, so for that we use a max-min composition or a max product composition. Okay, so just a little bit of going back to what we have done before. Let us say we have R1 and R2 as our relation matrix. Okay, so for max-min, sorry. So we treat these like in general matrices, but in place of a product, we are going to take the intersection, and in place of addition, we are going to take the union, right? So 0.1 into 1.0. So 0.1, you usually do the product in matrix. Here, in place of a product, you're going to write an intersection. So 0.1 intersection 1.0, comma 0.3 0.3 into 0 in the intersection 0, or you can just write it as plus, right? And then 0.1 intersection 0.0, sorry, not plus, it's union, right? So 0.1 intersection 0.0 and 0.3 intersection 0.3 intersection 1.0, right? And then we have 0.5 intersection 1.0 union 0.6 intersection 0.0. And then we have 0.5 intersection 0.0 union 0.6 intersection 1.0. And that is going to be, this is 0.1 union 0.0, and this is going to be 0.5 union 0.0, and this is 0.0 union 0.3, and then we have 0.0 union 0.6. So that is equal to 0.1, 0.5, 0.3, 0.6. So this is your other composition between R1O, R2, right? So this is for max min. So for max product, in place of this intersection, you're actually going to do the multiplication, but the union will be the same, right? I hope you all remember this this one. Can you all please do the max product for me? Just tell me the values. Sorry. Just a second. Any answers? Or do you want more time? Okay. Thank you, Janani, and thank you, Yamuna. Okay. So I'll just follow you guys. Okay. I'm not sure of the answer. Please cross check. But since both of you are giving me the same answer, so I think okay, it's right. Okay, I didn't do it by myself. So okay, right. So in this defuzzification, we have 5 different methods, right? We have discussed that in the last class, right? In place of the defuzzifier, we have these 5 methods, and we said we'll go through all of these methods, right? Okay. So one of the things are mean of maximum method. So mean of maximum method is, for example, let us say you have a trapezoid. Okay, let us consider having a trapezoid like this. So this is x1, this is x2, this is x3, and this is x4. Okay, and let us call this is as our highest membership function, right? So when I'm saying mean of maximum, so the maximum membership values that I'm having are here, right? In between x2 and x3. So that's the maximum I'm getting. So in that interval, right? So as the name suggests, we are now going to take the mean of these maximum values. So you are going to do x2 plus x3 divided by 2. So this is the mean, right? So this is in general. Okay, I hope you all understood the mean of maximum method. In the class, for the continuous function, for the continuous membership function, it is given. But here I'm discussing about the discrete. So, in case if you want to know more about the continuous ones, I prefer you to just go and look at the class notes. Okay, and then we have center of area method. So you take the entire area and then you find the center. So here you take the summation of the membership value. You take the membership value multiplied by this Z value. Okay. So where Z is the output dimension. So yeah. So far we were using X. Here it is given as Z. That's it. And divided by the summation of all the membership values. In case if you want to know about the continuous functions, then in place of the summation, what you have to do is you just have to put a integration, right? So integration up till n and mu c of zj into zj dz divided by integration of mu c z into dz. So that is how it is for continuous. Okay, and then we have the bisector of area. So as a name suggests, we are going to divide it into two halves. Okay, so the entire area is divided into two parts. So one is from alpha to 0 and other is from, sorry, alpha to z naught. So alpha to z naught and z naught to beta, right? And this area should be equal to this area. Okay, and how do you get the alpha values? You take the minimum value of z, and for the max and for the beta value, you take the maximum value of z. Okay, and the other types that we have are the smallest of maximum. So z SOM is the smallest of maximum, is nothing but the minimum value of z for which the membership function has its maximum value. For example, let us just go back to our trapezoid example, right? So here we have the maximum values for in between x2 to x3, right? I'm saying take the smallest. Smallest here in between x2 and x3 is x2. So your SOM is going to be um, x2. So the largest of maximum. So this is just the opposite of smallest of maximum. So here you take the maximum value of z for which the membership function has its maximum value. So again, if we trace back to our trapezoid example, in between x2 and x3, you have to take the x3 for this. Okay, so far clear? Okay. Uh, I see that Amber has asked a question. So when you say, okay, in additive, we do not need this defuzzification. That's your question, right? So you actually need defuzzification in both uh, additive and non-additive rule models. So okay, so in additive rule models, so you're basically taking the output of each rule and you're combining by adding them. Whereas in non-additive, you are not simply not adding stuff, but you combine them in a different manner. Okay, it might involve taking maximum or minimum of the rule outputs, or it might involve other techniques such as weighted average or other more complex fusion of results which are there, which we are not going to for this whole thing. Okay, so for example, let me just give you an example. So let us say you have two rules. Okay, let us say temperature is high, then output is large, and that is rule one. And in rule two, you have if temperature is medium, then the output is medium. So these are, let us say, these are the two rules. Okay, so if the fuzzy output for high is a fuzzy set that is representing large, and the same for medium. So when the temperature is medium, then your fuzzy set is representing medium. In an additive model, you would simply add the fuzzy sets for large and medium together to get a final fuzzy output. And since you're having a fuzzy output and you need a crisp output, right, you definitely need to use a defuzzification process. Okay, and the same is also for non-additive. So there also you have some set of rules and then you get fuzzy outputs, and for that again you have to apply the defuzzification process and then you get a crisp output. Okay. Okay. So okay, and now I'm discussing some of the questions from in additive we directly get crisp output. Amber, can you just give an example? Okay. So meanwhile, I'll be discussing some of the questions from uh, last class, okay, last term of this entire course. Okay. So the first question is, who is credited with developing the Mamdani fuzzy model? Anyone would like to answer? Yes, Amber and Yamuna, you are right. So the answer is Mamdani. So, which components constitute the fundamental elements of a Mamdani fuzzy model? Option A, evaluating rules. Option B, defuzzifying input variables. Option C, defuzzifying. Option D, aggregating outputs of fuzzy rules. Option E, all of the above. Yes, Yamuna, Amber, and Janani, you all are right. It's all the above. So first, we fuzzify the input variables, and then we evaluate the rules, and then we aggregate the outputs of the fuzzy rules, and then we do the defuzzification process. Right. Okay, for your third question. What was the initial application of Mamdani fuzzy model? Yes, Amber, Janani, and Yamuna, you all are right. So the first one was controlling a steam engine and a boiler combination. Okay. So in the context of Mamdani fuzzy models described as we have a rule, okay, if x is a, then y is b, and then we have a fact that x is a dash, and the conclusion is y is b dash. So which type of Mamdani fuzzy rule is this? Yes, Janani and Yamuna, you both are right. So it is C, single rule with single antecedent. So we have only one rule and then we have only one conclusion, right? Okay. Um, no. So let us consider a Mamdani fuzzy model with a single rule and multiple antecedents, and it is defined in such a way, right? So if x is a and y is b, then z is c, and then we have a fact x is a dash and y is b dash, and then we have a conclusion saying z is c dash. Okay, so these were exactly not discussed during this session, but if you go through the lectures, then you will be able to understand this. Okay, so when you are given weights W1 and W2, and then what will be the value of weights obtained using max min composition for the truncation. So when you are given max min, then you take the minimum of 0.7 and 0.5. That is, you take the minimum value in between both the weights, right? So you take the minimum of 0.70 and 0.50, which is equal to 0.50. So Amber, Yamuna, you both are right. It is 0.50. So for the same question which was given in the previous one, what will be the value of the weight out obtained using max product composition for the truncation of C? 0. Okay. So when we take max min, we have taken the minimum of the weights. So when we are taking max product, you take the product of both. So you take the product of 0.70 and 0.50, which is equal to 0.35. Amber, Janani, and Yamuna, you all are right. Okay. Then we have the seventh question. So, if the aggregated output of a Mamdani fuzzy model is a trapezoidal shape output defined using parameters 2, 5, 7, and 8. Okay, so let us draw a trapezoid. So 2, and then let's say this is 5, and then let's say 7, and then let's call this as 8. Right? So we have the parameters 2, 5, 7, and 8, and with the maximum membership function value to be 1. So this part is 1. So the maximum values are 1. What will be the defuzzified crisp output value using mean of maximum? So we have discussed this. So for the mean of maximum, let us take all the z values where or the X values where the membership value is highest. Membership value is highest in between the values 5 and 7, right? So the range is 5 comma 7, right? So now we have to take the mean of these values. So the mean is equal to 5 plus 7 by 2, which is equal to 6, right? So the answer is 6. Okay, I lost track. Well, yes, Amber, Yamuna, and Janani, you all are right. Okay. So for the same question, I'm asking you to find the smallest of maximum. What will be the smallest of maximum? A, C. Yes, Amber and Yamuna. Amber, Yamuna, and Janani all are right. So when we say the smallest of maximum, the maximum values are lying in between 5 and 7, right? So the smallest of all of these values in between 5 and 7 needs to be taken. And hence we take the value 5, right? Okay. And the last question for today. For the problem statement given in question 7, what will be the defuzzified crisp output value using largest of maximum? So our maximum values, the maximum values of the membership functions are for the values 5 to 7. And now we want to know the largest one of those. So which is going to be 7. Uh, Yamuna, Amber, and Janani, you all are right. Okay. So far, any questions in this assignment ka stuff? Any questions in this? Okay, thank you, Yamuna and Amber. Okay, do you want similar questions to be asked or it's all right? If you want similar questions, you have to give me some time. If not, it's fine. Okay, then just give me 10 minutes. I have to open this. So currently I'm not using my laptop. I'm using someone else's. So it's just taking me some time. I have to log into everything. Okay, just give me some time. So just a trick question which I haven't mentioned. Okay. So here we have these five methods for defuzzification, right? So which of these method, like there is one method which is most commonly used for defuzzification in a Mamdani fuzzy inference system. Once more, like you told earlier that you will be holding a problem solving session after 12 weeks. However, can you discuss? So I do have only the last year's assignment questions. I do not have the ones before that. So yeah, you can share the those questions with me. Maybe I can take that class. Okay. Okay. So in these declassification methods that we all have, all these five methods, so which one do you think is the most commonly used? So let's just call them one, two, three, four, five. Okay. Any guesses on which one is the most commonly used defalsification method? Yes. Yes, Amber and Dhruv, you both are right. It's the centroid of area. Okay. Ah, and so in a Mamdani fuzzy model, the output of each rule is represented as fuzzy set, crisp set, crisp value, probability distribution, membership function, and a numeric value. Any answers? Okay, Amber, any more answers from anyone? So again, uh, output of each rule. We are talking only about rule. I'm not asking for the output of the overall thing. Just the rule. Okay. No. So when we are dealing with rules, the output is going to be a fuzzy set. Okay. So it's a fuzzy set. Okay. So let us say, for example, the temperature is high, the output is high, the temperature is medium, the output is medium. So that is a rule that I'm imposing. Okay. So when I say an output for it, I'm still going to say the output is going to be high or medium. I'm not going to say any other values or any other things, right? So I'm still going to keep it as a fuzzy value. Sorry, fuzzy set. Okay. So this is for rule. Okay. Is this one clear? Okay. Our next question. It's the same question again, but okay. Which of the following is not a typical feature of Mamdani fuzzy inference system? Okay, option A, fuzzification of fuzzification, rule-based inference, aggregation of rule output, linear regression of, sorry, for output estimation, defuzzification, Amber, Yamuna, and Janani all are right. It's linear regression for output estimation. So the other four are the features of Mamdani, the process that's involved in the Mamdani fuzzy inference system, whereas the linear regression for output estimation is not. Okay, input can be crisp or fuzzy, but the output should be only fuzzy. So the output of the rule is going to be fuzzy, okay, but the overall output is going to be crisp. Okay, the output of the rule is always a fuzzy value. These all are same. I'll check for more. Okay, another question. In the Mamdani fuzzy inference system, the fuzzification process involves option A, mapping crisp output to fuzzy sets. Again, mapping crisp inputs to fuzzy sets. So, aggregating fuzzy outputs, defuzzifying fuzzy output, and evaluating the rules. Okay. Yamuna, Janani, and Amber, you all are right. The answer is B, mapping the crisp input to fuzzy sets. So always see if mentioning output or input, okay, don't get confused there. Okay, for the same options at the top in the previous question, question 12, what is the role of defuzzification process in Mamdani fuzzy systems? I'll give another set of options. Combine fuzzy outputs, map crisp inputs to fuzzy sets, convert fuzzy output into crisp value, evaluate fuzzification of inputs. E, define membership function. Yes, Ambar, Yamuna and Janani, all are right. It is to convert the fuzzy output into a crisp value. Okay. Okay. 14, right? So, which of the following methods can be used to combine multiple fuzzy outputs in Mamdani fuzzy inference system? A, mean of maxima or mean of maximum, additive aggregation, C, weighted out. Okay, this one is not taught to you all, I guess. So, okay, let's just skip this question. Okay. Let's just skip that question. Okay. Okay. So in Mamdani fuzzy model, the rule base is usually composed of which type of rules? Option A, if else. Option B, probability based. Option C, if then. Option D, linear regression equations. It's simple, right? If it's if then rule. Okay. I'm not asking them like questions, but I'm just going to give some statements. Okay, some statements that might be useful for you, but I'm not sure in terms of assignments and all of that. But this Mamdani fuzzy systems are most suitable when you require some sort of a human reasoning and decision making under uncertainties are required. Okay, so whenever you want to get an outputs like high, low, good, bad, all such things, then Mamdani fuzzy system can be used. Okay, but when you require exact values, then Mamdani fuzzy system is not your thing. Okay. And one of the main disadvantages of using this Mamdani fuzzy system is that the inference time is high. Since there are a lot of rules and lot of complexities associated with the rule-based system, the Mamdani fuzzy system is usually the inference process is very, very slow. Okay, so that is one of the main disadvantages of using a Mamdani fuzzy system. Okay, so these are some statements in between. Yeah. Okay, so the same questions keep repeating. So one such question is, what is the entire process of the Mamdani fuzzy group? So like the second question. Okay, so after what comes what is one type of question, and what all are there, what all are not there, all such kind of questions you can see more. And apart from that, yeah, those are that is the most asked questions I can see. Okay. Yeah, that's all. So those are all the questions that I have with me. Okay. Any questions? Okay. If there are no questions, this is where I end the class. Okay. But if there are any questions, you are free to put them in the chat box. I'll be here till 8. Okay. So yeah, thanks a lot for joining, everyone. So with this, upload the PDF. I have already uploaded till week 10. This one I'll upload along with the recording of this class. Okay. Uh, yes, Dhruv, you can leave. If you have no questions, you can leave. But yeah. Okay. Thank you, Amber. Thank you, Yamuna. Thank you, Janani. Yes, Amber, what is the questions that you have in question 6 and question 7 from week 7 assignment? Okay, let me just open the sixth question. Okay, so the sixth question is, which property is not exclusive to fuzzy relation? Option A, law of contradiction. Option B, idempotency of intersection. Option C is commutativity of union. And option D is associativity of composition. Okay, so law of contradiction is basically it's statement saying that both cannot be true and false at the same time. And this law is not exclusive to fuzzy relation. It is applied. It applies to a classical or a crisp relation, but okay, and then we have idempotency of intersection, so which is basically A intersection A is equal to A, and which we have proved for fuzzy relation. And commutativity of union, we have A union B and B union A, and that is both equal, and we that holds good for both crisp as well as fuzzy relations. And associativity of decomposition, so even if you take A, B together or B and C together, it is going to give you the same output. So that also holds good for a crisp relation. So the last three definitely holds good for a crisp relation, and law of contradiction is the one that does not follow, like fuzzy set do not follow the property law of contradiction. Which property does not hold for both fuzzy and crisp relation? That's the seventh question. Law of excluded middle, involution, distribution of union over intersection, none of the above. So, in a way, the law of excluded middle says that either P is true or the negation of P is true. Whereas in a crisp logic, that this law holds universally. But whereas in a fuzzy logic, it's not the same. It because fuzzy logic deals with degrees of truth, right? It can be high, medium, low, all of other things. So a preposition can have a true value that is somewhere in between 0 and 1, and the negation of the fuzzy proposition will also have the same range from 0 and 1. So for fuzzy logic, it's possible to have a situation where neither is a proposition nor is a negation, which is fully true or fully false. So half true, half false is also possible, which actually violates the law of excluded middle. And hence, law of excluded middle does not hold good for both fuzzy and crisp. Okay, so yeah, that's my opinion on these two questions.